Today, I'm pleased to introduce David Naylor. David is a PhD student at Carnegie Mellon University, where he's advised by Peter Steenkist. His primary research interests are computer networking, security, and privacy. He's also interested in web measurement and performance. So let's give a warm welcome to David for his presentation today.
Thank you. Okay, so thanks for the intro. It's really exciting to be here. I usually come to these talks, and so it's fun to get to give one to close out the semester. And what I want to talk about today are network middleboxes, and specifically how we can include them in secure communication sessions. So normally when we think about network communication, we just think about the two endpoints and we say, okay, we have some kind of end-to-end connection between them and there's a bunch of stuff in the middle, but we'll let the networking people deal with that stuff. But it turns out there's a lot of stuff in the middle, and some of it we do need to worry about. And so in particular, I'm talking about devices called middleboxes, which are special purpose devices in the network that process our traffic beyond just basic IP forwarding. And it turns out there's actually a lot of these. So most networks have roughly the same number of middleboxes as they do routers and switches. And these middleboxes do a bunch of good things for us. So they improve performance by doing load balancing or caching. They can help us with our data usage by, say, compressing. They can improve security by doing intrusion detection or virus scanning. And then they can add other types of functionality like parental filtering. So this is great, but lately middleboxes have run into a problem, which is that as we start to encrypt more and more of our network communication, they're becoming blinder and blinder. So when we encrypt a session, the middleboxes can't see our data, so they can't do their jobs anymore. So if I go and turn on TLS on my web server, my site is instantly no longer cacheable. Now, don't get me wrong, I'm not arguing against encryption. Encryption is great, and from a security and privacy standpoint, it's absolutely what we should be doing, and these recent efforts like Let's Encrypt are wonderful. But at the same time, this actually is a real problem, and we need to come up with some way to address it. So in my talk today, I want to talk about potential ways we can keep the security and privacy benefits of encryption, but at the same time not give up the performance and functionality benefits we get from middleboxes. So a quick aside, for a long time in the networking community at least, middleboxes sort of got a bad rap. That's sort of disappearing. People are okay with them now. But sometimes people still wonder why. Why are you doing this? Middleboxes just break things, and they should go away, and encryption is finally making them go away. This is good. So I don't think that's entirely fair. If you stand back and squint, I see roughly 3 categories of middleboxes. So the first ones I'll call value-added services. These are things that provide tangible benefits to end users, so they actually choose to opt into these. So a good example of this is if any of you use Android, in Chrome on Android, there's a feature in settings called Data Saver, and if you go and click that on, what it does is it sends all of your unencrypted HTTP traffic through a proxy at Google that does a bunch of things, but primarily it scales down images and converts them to a smaller format so that you can save mobile data. So that's an example of a middlebox of this first class. The second category, I'll call them administrator mandated. So these are things that help your network operator run your network, and even though they might not directly benefit end users, they're not going to go away anytime soon. Now the third category, for lack of a better term, I'll call them unauthorized middleboxes. These are things that you don't know they're there, you don't know what they're doing, they're not directly helping run the network, they're not directly doing anything good for you, and they might be doing nasty things. So an example of this is when Verizon got caught inserting super cookies in all of the HTTP requests on their network. Okay? So these are not the middleboxes I'm talking about. We don't like these either. So everything I'm talking about in the rest of this talk, we're focused on these top 2 categories of middleboxes, where at least one of the endpoints wants it to be there. Oops. Okay, so we want encryption and middleboxes. So at a high level, there's sort of 2 approaches you could take to do this. So first, you could try to make middleboxes that can actually operate directly on the encrypted data so that it never needs to be decrypted. And there actually are people doing this right now. So there have been a couple recent papers actually by Justine Sherry, who's going to be joining us as CSD faculty here in the fall, looking at how we can have Middleboxes operate on encrypted data. But the problem with these approaches so far is that, one, they're limited to middleboxes that do pattern matching things like intrusion detection, and two, they're so slow and they use so much data that so far they're not practical. So in order to start up a connection with their system, you need to transmit 12 gigabytes of data before you can even begin your connection. So there's some work to go here first, but that's a promising future direction. But in the meantime, that means the only other option is to somehow give the middleboxes access to the data that we have encrypted. So that's what I'm going to talk about in this talk. Now, first you might say, can't we just use TLS? Do we really need something new? Can't we just play some games with certificates or something? And this actually is done today, especially in corporate networks, but I argue that the way it's done today is broken. So what happens today is, let's say you have your company laptop, and before you get it, the IT staff installs a root certificate on that laptop. Then when you go to open up a connection, let's say to foo.com, the firewall, let's say they want to have their firewall inspect all of the inbound and outbound traffic. And so on the fly, it's going to fabricate a brand new certificate for foo.com, and it's going to sign it with the key in that root cert that we added to our trust store in step 1. And so because it's a certificate in our trust store, the client accepts the fake certificate, it finishes the TLS connection, thinks it's talking to foo.com, and then in the background, the firewall opens up a second connection to the real server and just pipes the data back and forth. Now, I argue that this is broken, and here's why. So fundamentally, TLS was designed for exactly 2 parties. And so this causes some problems in this scenario. So first, TLS gives you no mechanism for authenticating additional parties like middleboxes. So in that example, we didn't get a certificate for our company's middlebox. We had no way of verifying that it was our IT staff who put it there. Secondly, the client has no security guarantees past the middlebox. So in my picture, I showed a second TLS connection on the other side of the firewall, but in reality, we have no way of knowing at the client that that's the case. Maybe the firewall didn't use encryption on that second connection, or maybe it did, but it didn't properly verify server certificates. So we still see the lock in our browser, but now it's basically meaningless. And then the third problem is the middlebox, in this case the firewall, got full access to all of our data, so it could see everything and it could change anything. And we didn't know that that was happening, and it might not be necessary for the middlebox to have that much access. So for these reasons, we don't think that TLS by itself is equipped to handle this. So I'm actually going to amend my goal statement here. We want to give middleboxes access to our encrypted data in a controlled way. So today I'm going to talk about 2 projects I've been working on, and yeah, question?
Why you cannot authenticate the middleboxes?
Why can't you authenticate them?
Yeah.
So you can, and we will in these 2 protocols. It's just TLS by itself doesn't give you a way to see both certificates and authenticate both the server and the middlebox. So you could get the middlebox's certificate instead and verify that you connected to your company's middlebox, but now you're trusting it to in turn verify the server.
Get the middlebox, right?
Sorry, say that again?
So you do authenticate the middlebox, you just don't do it for the next server, right? So it's just not clear for me.
You could authenticate the middlebox, but at least I think the way it's typically done in this scenario is the middlebox sort of makes up a certificate where it pretends to be the server. So you could argue that you're sort of indirectly authenticating the middlebox because that fake certificate was signed by your IT staff's key, but you're not, it's sort of a hack, I would say. TLS wasn't exactly designed to be used that way. So we want to do something cleaner where you can cleanly authenticate both the middlebox that's in the middle and the server you connect to at the end. So I'm going to talk about 2 projects. The second one is still ongoing, so I have a little bit less to say about that one. But in both of these, we explore with different definitions of what security semantics you might want for a secure session that has middleboxes in the middle. So I have controlled up there in quotes because this is sort of a new topic and it's not clear exactly what security properties we're going to want. So we played around with a couple possible definitions for security. So as a quick aside, I want to talk about the security properties we're starting with. So I don't think I need to talk too much about this for this crowd, but just as a quick reminder, when you do a TLS handshake, you're getting 3 security properties out of that connection. So first, you get data secrecy, because all the data is encrypted between you and the other endpoint. You also get data authentication, so each TLS record has a MAC, and so that means whenever you receive a TLS record, you can make sure that it hasn't been modified in flight since it left the other endpoint. And then you also get entity authentication, so you verify the server's certificate, and you make sure that you're talking to the server that you mean to be talking to. So first, let me start with a protocol I developed in collaboration with a bunch of awesome people at Case Western and Telefónica Research. We call it Multi-Context TLS, or mcTLS. And the idea is to provide access control for Middleboxes. So for mcTLS, the security properties that we want, so first of all, we want to maintain the three security properties TLS was already giving us. So we're going to use the standard TLS protocol as a base, and we're going to make a few tweaks to allow us to add extra parties in the middle. And when we do that, we want to additionally provide 2 new security properties. So first, the first one, I'm calling it here visibility and control. What I mean by that is that both endpoints know about all the middle boxes, and both of them need to agree that those middle boxes can be there, otherwise the handshake fails. And the second new property is, I'm calling it least privilege. This is the idea that we want to provide access control so that these middle boxes get access to the minimum amount of data that they need to do their job and nothing more. So I'm going to talk about how we achieve these, and I want to start at the end with least privilege. So as a simple example, if we look at a few common middle boxes listed here on the left, and let's just talk about web traffic for now. So you can sort of logically think of HTTP traffic as having 4 pieces, right? There's a request and a response, and each of those has some headers and a body. So we have headers, body, headers, body. And so what you see in this chart is a hollow dot if the middle box needs read-only access to that chunk of the data, and a solid dot if it needs read-write access. And what you should notice is that only 2 of these middle boxes need access to all 4 segments of the data. The others just need selective access to certain segments. And only 2 of these need write access to any segment of the data. So this suggests that access control could be an effective way to sort of limit how much power we give to the middle boxes. So we designed a new abstraction for applications using TLS that we call Encryption Contexts. And the high-level idea is when an application sends data, it now additionally specifies a tag. And that tag identifies a set of permissions, effectively. So you could almost think of it as we have like different classification levels, like classified data and top secret data. And each middle box, each time we send a chunk of data, we tag it as top secret or whatever. And each middle box then gets a particular classification level. It can read things up to this point. So if we keep going with our example of web traffic split into these 4 chunks, so the request headers, request body, response headers, and response body, you could imagine saying, okay, maybe I have a parental filter, and I want it to have read-only access to the request headers so that it can see the URL I'm requesting and decide block or don't block. But it doesn't need access to anything else, and it certainly doesn't need to change anything. And then maybe we also have a compression proxy that we want to shrink images because we're on our mobile phone and we're worried about data usage. So let's give it read-write access to the response, but we don't want it interfering with the request. It really doesn't need to touch that. So this is the abstraction that we want to provide to applications. And the way we do that is by modifying how the TLS record layer works. So in vanilla TLS, you do the handshake and you wind up with a shared session key between you and the server. And that key is used both to encrypt the data and to put a MAC on each record so you can detect if there were unauthorized changes. So in mcTLS, we add a couple new keys. So we call these keys the reader key, the writer key, and the endpoint key. And so the way we use those is we start with the reader key, and that we do the normal data encryption and a MAC. And so the point is, so first of all, any middle box with read access gets a copy of this key. So I'm not going to show you the handshake, but we added a few steps to the handshake where we exchange these keys, and we give them to the middle boxes that they should go to. So the read-only middle boxes get the read key, so that means they can decrypt the data and read it like they should be able to. And they can also check this MAC to make sure that third parties, like people sniffing our Wi-Fi in the coffee shop or whatever, can't make unauthorized changes. But the problem is if we stop here, if we don't have these two MACs, we just do this, that means a reader has this key, so it could make unauthorized changes to the data and compute a new MAC that's valid. So we want to prevent that, so that's where the writer key comes in. So this is an additional key that is given to any middle box with write access to the data. So the readers don't have the orange key. So that means if a reader makes a change, re-encrypts the data, and makes a new blue MAC, they don't know how to compute a new orange MAC. So when it gets to the next hop, we'll catch it. And then likewise, we have another MAC. It's the same thing again, only this one is only known by the endpoints. So if any writer middle boxes make changes, we can see that. Now that's not a security violation. They had write access, they're allowed to. But in some cases, maybe the application just wants to know whether the data it's getting has been modified since it left the other endpoint. Okay, so far, this allows us to control read and read-write access separately. And so now all we do is we have multiple sets of these keys. So if we want to break our data up into different pieces and have different permission levels for those different pieces, we just have one set of these keys for each encryption context. Well, the endpoint key is the same, but there's a separate reader key and writer key for each encryption context. So let's look at a quick example. So let's say we want to talk to a server, and in between we want a parental filter and a compression proxy, like I was saying earlier. So the handshake process now generates all of these keys. So I'm sticking with this example where we have sort of 4 logical segments to the data. So for each segment, we have a reader key and a writer key, and then there's the endpoint key hanging out here at the end. So the endpoints, of course, get all of the keys. The endpoints get access to everything. But the parental filter, we're only going to hand it the read key for the request headers so that it can look at the URL that's being requested and either drop the connection or let it through. And the compression proxy gets the read and write keys for the response. So it needs to be able to write the response so that it can write the compressed version, and it needs the headers so it can write the new size, the new content size. So I don't have time today to actually walk through the handshake and show how these keys are distributed, but if you have any questions, just grab me and I can walk through it with you. But this is the high-level idea. At the end of the handshake, this is the state of the world. These are the keys that everyone has. Okay, so that's how we implement access control, so we can sort of tamp down on the permissions that the middle boxes have to the minimum level they need to be effective. And then the second goal we had was we want to make sure that both endpoints are in agreement about what access level each middle box has. And so the way we do that is those reader and writer keys I showed you are actually generated in 2 pieces. So the client generates some of the key material that's used to create those keys, and the server generates the rest. And during the handshake, each endpoint sends its chunk of the key material to each middle box. And so only if both endpoints agree that the middle box can be there and it can have a particular context key, only then will the middle box learn the context key. So the server can't sort of unilaterally give the middle box access to content if the client doesn't send its portion of the key material as well. Okay, so that's how we ensure that both endpoints are in agreement about what the state of the session looks like. So that's what I wanted to say about mcTLS. Are there any quick questions about that before I move on to the second part? If you're still thinking, you can ask at the end too, of course. But this is just sort of a natural break point. Okay, cool. So this was one example of a definition of security that we could adopt for connections with middle boxes. For this next protocol, which is tentatively called mcTLS, which is just so that I can abbreviate it mbTLS, and now I just need to do mATLS and I can graduate, we explored a different definition of security. So this is a project I've been doing with Microsoft Research, and sort of the impetus for this project was a particular set of design goals that Microsoft had. And so the two important ones are, one, they wanted to be able to support legacy clients. So they want clients to be able to connect to Microsoft services, and they want to be able to insert their own middle boxes into those connections without upgrading any software on the clients. Now, you'll immediately notice that this departs from the security properties we had for mcTLS, which required both endpoints to be in agreement, because now if we support legacy TLS clients that don't even know middle boxes exist, clearly we can't get their permission to do this. So we're trading off joint control to get incremental deployability. And the second thing is they want to be able to support new deployment models. So what do I mean by that? So there are two recent trends in middle box deployments. The first I'm calling middle boxes as a service. So people are looking at deploying middle box processing as a service in the cloud. So companies would offer, say, hey, we do virus scanning, we do intrusion detection, et cetera, et cetera. You just pipe all of your network's data to us first, we'll process it, then we'll send it back to your network, and you don't need to deal with it. So we get economy of scale here because each network doesn't need to buy their own expensive set of middle boxes, and they also don't need to deal with the management burden of keeping these things upgraded and configured. And this actually is a big deal. So there was a study of network operators a couple years ago, and they cited middle box management as one of the biggest burdens they have, because today these are custom devices. They're from different vendors, and you have to learn how to manage and operate each one. Okay, so people are looking at outsourcing this to the cloud. People are also looking at deploying middle box type services at the edge, so like in customer ISPs, sort of like CDN nodes in individual ISPs, so that you get low latency access to the customers. The responses can be faster if you don't need to talk to the server. And also, if you can cache big chunks of data there, you don't need to pay to transmit as much data all the way across the internet. Now, the important thing about both of these deployment models is that the software owner and the hardware owner are no longer the same. So if we have a service provider like Google or Microsoft that wants to run some of their middle box processing in the cloud, they're basically handing their middle box software to some cloud provider and saying, here, run this for me. So it's their software, but somebody else is managing it. And from a security perspective, this matters because we might not completely trust those cloud providers. So we want to, if you're Microsoft, you want to keep your customers' data confidential. So to make this a little more concrete, we've added a new player to our trust model. So I don't know if you can see the shading here. Green means trusted, red means untrusted. So the green components are the ones that we want to be able to access our session data, and the red ones we don't. So in case the colors don't show up, the only thing that's different is the middle box hardware is colored red. So that means we don't completely trust the systems that the middle box software is running on, but we do trust the software that's running. So let's say this is some custom middle box software that Microsoft ships off to ISPs and says, hey, please run this for us. And so what this means is that the traditional mechanisms that we use in TLS to get properties like data secrecy and data authentication are no longer good enough. So one particular problem is that TLS session keys and session data are visible in RAM on the middle box, right? So TLS records come in on the wire and they're encrypted. That's good. But as soon as the application decrypts them, that session data is just sitting there in RAM, so the middle box provider can see it. And the session keys are also there, which means they could extract those keys, forge TLS records, and send them to either endpoint, and they'll have a valid MAC. And the second problem is that authentication also gets trickier. So normally the way we do authentication in TLS is with certificates and private keys, right? And when the system you're talking to is sort of owned and managed by one entity that you trust, the fact that that server has the private key that matches the certificate is sort of enough to convince you that the software you've connected to is legit. Because we assume that the server is under complete control of say Microsoft or Google, and so the fact that they put their key on that machine means that we can trust any software running on that machine, essentially. But the problem is that's no longer the case here, because now we have machines that are operated by someone else. They might be running software for a lot of different people, and so even if we provision it with a copy of our certificate and private key, that doesn't really mean anything. It just means that this hardware has a copy of the service provider's private key. But they could, instead of running the Middlebox software that Microsoft gave them, they could run some other software, and they have the key in the certificate to prove that they're running the correct software. So the way we're going to deal with this is by turning to trusted computing. Specifically, we're going to use Intel SGX. So in case you're not familiar with SGX, it's an extension to Intel's x86 instruction set that gives you basically two features. So the first is you can now run code in secure execution environments that Intel calls enclaves. And an enclave is essentially an encrypted region of RAM where your programs, your program code and your stack and heap live. And so that means anytime that data leaves the CPU, it's encrypted before it goes to memory. So as long as you trust the physical CPU package, the rest of the hardware on your system and the rest of the software on your system can all be malicious, and you're still safe. And then the second feature it gives you is called remote attestation, which is the ability to prove to a remote party that the enclave is running correctly and that a particular piece of software is running in the enclave. So like, say, a hash of the binary that's running in the enclave. So let's look at how we're going to use SGX to help us fix these problems. So first of all, of course, the first problem was that the keys and data were visible in RAM, and so now, of course, we just move the Middlebox software into the enclave, and now that's all encrypted, right? So encrypted TLS records come in on the wire, they're still encrypted. They go into the enclave, and inside the enclave where it's safe, they get decrypted. So that means, even though the data's decrypted, it's still in an encrypted region of RAM. So from the perspective of the Middlebox provider, it's still encrypted. Do the processing in the enclave, re-encrypt it into a new TLS record, and then send it back out to the network. The other problem we had was authenticating that we were talking to the right software, and so now, of course, we use remote attestation for this. So now, when we handshake with the Middlebox, we also do an SGX attestation, which tells us the exact identity of the software we're connecting to. So this is the high-level idea of what we're doing in mbTLS. I just want to show you a super high-level sketch of the handshake. There's a bunch of details, but at a high level, this is what's going on. So we do a normal TLS handshake end-to-end between the client and the server. And concurrently, for each Middlebox, we do a second TLS handshake with one of the endpoints. So we assume that each Middlebox is associated with one endpoint or the other. And so in this case, let's say it's a server-side Middlebox. So we do a separate TLS handshake with that endpoint. And we also, with this handshake, do an SGX attestation. So the Middlebox proves to, in this case, the server, that it's running in an SGX enclave, and it also proves that this is the identity of the code that's running. And if that attestation passes, then the server provides the session key to the overall primary TLS session. So you'll notice two things here. First of all, these are both standard TLS handshakes. We didn't modify the TLS state machine. We just added some stuff on top, and we do multiple handshakes. And so that's important because it sort of makes it a little easier to reason about the security properties that we're getting and that we're not completely screwing everything up because we're just adding sort of a thin layer on top and doing normal TLS handshakes underneath. And the second thing you'll notice is that in this example, there's no communication happening directly between the client and the Middlebox, no extra TLS handshakes. And so this is how we support legacy clients, right? So in this case, the server wants to add this Middlebox. This could be just a normal TLS 1.2 client. It doesn't need to know anything about the Middlebox. The server takes care of all that in this example. Okay, so the protocol itself is simple enough. It doesn't look like there's a lot going on here. The primary challenge here is actually the software architecture on the Middlebox. So in particular, SGX sort of severely restricts the types of things you can do. And one of the things you can't do from inside an SGX enclave is network I/O. And Middleboxes obviously need to do a lot of network I/O. So that means you need to take your Middlebox software and split it into two pieces and have some of it live outside the enclave in the untrusted world, and it handles all the network I/O that the Middlebox needs to do. And then when it gets TLS records from the network, it needs to somehow pass them into the enclave where they can be decrypted, processed, re-encrypted, and then passed back out to the untrusted part where they go back out to the network. And so we were concerned about performance here. How fast can we do this? So we built a prototype. We used OpenSSL and made a few modifications to it, and we combined that with the Intel SGX SDK. So we have a version of OpenSSL that runs in the enclave and includes attestation in the handshake. And we implemented a really simple HTTP proxy and ran some performance tests. So like I said, this is an ongoing project, so we're still working on finishing the prototype and evaluating it more thoroughly, but I have one plot I can show you today. So this is a throughput comparison. So we have a non-SGX, just a standard version of our proxy. That's what you see in orange. And what I'm showing here is the throughput normalized to the non-SGX version. And the blue line is our proxy running inside the SGX enclave. And what you see is throughput as a function of the size of the messages that we're piping through. So the smaller the messages, the more sort of per record operations we need to do. The bigger the messages, that sort of gets amortized. But what you'll notice is that in all cases, the worst we do is about a 10% drop in throughput compared to the non-SGX version. So we're actually pretty happy with this. We're still working on this to see if we can make it better, but we weren't really sure what to expect, and we're pretty happy with these numbers. It sort of indicates that you maybe could reasonably implement some Middleboxes in SGX and have reasonable performance. Okay, so that's still ongoing. Talk to me in a couple months, and I can give you an update on that. But zooming back out, that's what I wanted to tell you about mbTLS. And again, both of these, remember, were different attempts to explore ways we could bring Middleboxes into our encrypted sessions so that we can still have encryption, but also still have the benefits of Middleboxes. And so we played with a couple definitions for what security could look like in those contexts and implemented them. mcTLS is open source. You can find that on my GitHub page. mbTLS, we're still working on it, and I need to talk to Microsoft, but hopefully we'll make that open source too. So that's all I have for you today. And I would love to answer any questions about either of these projects. Thank you. Or Middleboxes in general.
Question?
Yeah.
Comment about the scalability for the first one. So as I understand, you have to create pairs of keys for each end host and each server, right? So
right.
What kind of impact does that have?
That's a very good question. I don't have the plot with me. So we saw. So you're right. So the endpoints need to do extra crypto operations during the handshake to generate all these keys and send them to the Middleboxes. And so in our tests, we saw anywhere between, I think, a 17 and 20-something% drop in the number of new handshakes per second that the server could handle. And that's if we're not doing any other processing, we're just opening and closing connections as fast as possible. Now, in some cases, you could imagine a lot of servers might say, hey, this is sort of this is the client session. It can do whatever it wants. If it wants to add Middleboxes, that's fine with me, and I don't care. And so we have a mode of operation where the server can say, I don't actually care. The client can add whatever Middleboxes it wants, and it has to generate all of the key material and distribute it, and I'm going to stay out of it and basically just do a normal TLS handshake. So if the server wants to give up its control about which Middleboxes can be in the session, it can sort of choose not to do any of this extra key generation, and we push that all to the client. And we sort of assume that for clients, you're not making that many connections, so you're not really going to care. But yeah, if the server does care, it does drop the number of connections that you can handle. Yeah?
So this is not really a technical question, but how do you feel about mbTLS in terms of the lack of transparency that's being offered to clients that connect to servers that use it? So like in your initial work, it was very clear that you favored the transparency, that you thought this was good. And now Microsoft is saying, well, we should trade this off because deployability is simpler.
Yeah.
But you're also under the idea that you're connecting to a service that's going, you're not just talking to that service, you're talking to that service through all of his buddies. And you don't really, there's an opaqueness as to what's actually taking place. So how do you feel about that?
Yeah, no, that's a great question. So, we did talk about this a lot, and we decided. So, one of the biggest concerns with transparent middle boxes are middle boxes that neither endpoint knows about. Things that your ISP throws in, like the Verizon supercookie thing. And so we still don't support those, right? Even in mbTLS, one of the endpoints needs to add it. And so we sort of took the stance that these are the processing that, say, Microsoft or Google or whoever the service provider wants to do with these middle boxes is stuff that they could have done that in their data center anyway, right? You could put you could sort of offload the TLS processing to some edge box that does the decryption at the edge of the data center and still do this processing on different machines in the data center. And so you're already sort of placing your trust in these companies to do the right thing with your traffic. And so we decided that it wasn't too much of sort of an extension to trust them to do this processing off-site if they're doing something like this, to be careful about how they do it. Now, I mean, this is still a research project. I'm not saying Microsoft is about to deploy this tomorrow or anything. I think we're still far away from that. So there's sort of time to think about this and make sure that we're handling everything correctly and that your data really is safe. But we sort of decided that these middle boxes, in this case, are sort of a logical extension of one of the endpoints anyway. And so if you already placed your trust in that endpoint to talk to them in the first place, it wasn't too much of a leap to trust the middle boxes that they like. Yeah.
You see the need for the Intel SGX as sort of a barrier to deployment? Because I mean, as far as I know, a lot of these middle boxes are special purpose hardware that are made to go real fast.
Right.
And so it seems like SGX is it's a more complex architecture for some of these middle boxes.
Yeah, no, that's a good point. So I think in a couple years that will be less of an issue because there's been this trend lately. So if any of you pay attention to the networking world, there's this trend called NFV, or Network Function Virtualization. And so that's the idea that all the security stuff aside, we're already sort of moving towards not having special purpose hardware devices for middle boxes anymore and just having generic software architectures where we just have normal x86 machines that run different middle boxes in essentially VMs so that we can sort of share the load across a pool of common servers. So that's already the direction that the networking folks are taking it, and so we think that will sort of line up nicely with when we have SGX on those CPUs, we can just do this. Yeah. Anything else? Awesome. Great. Thank you all for coming, and I'm local, so if you want to talk about this more, just ping me and we can set up a time to chat. Thank you.